Hello everyone, welcome to the Quantum Mic, and it is Olympic season. That's right, it is time to watch people skate across ice and snow at incredible speeds, doing fantastic acts of athleticism, and I thought, well, what a better way to, celebrate the Olympics than to talk about the science of some of the Olympic sports. I know, it's brilliant. It's definitely not a ploy to go ahead and take advantage of the algorithm. All right, so today I have done some research on 3 Olympic sports. We're going to talk a little bit about the physics and science that is involved in those 3 sporting activities. I have got my Team Canada scarf on. Go Canada. And let's begin. Ski jump. That's right. The sport where people go ahead, put on very, very large skis, start at the top of a hill or a ramp, and accelerate down and then jump and try to fly like an eagle or a flying squirrel all the way across before landing on the ground, right? They're trying to get a very far distance while, of course, having what's called aerial style. I'm not an expert in ski jumping anyway. Never really been something that was very popular for me to watch, but it's a very interesting sport. There's some interesting science and physics all involved in it, and I like watching it during the Olympics. But, the Olympics is the time to watch interesting little sports that aren't very popular back home. So, how does ski jump work? Okay, there is a curved ramp at which the athletes start at the top. They will glide down said ramp with their skis before jumping off at the end, and then and putting their body in this V-shaped form. Maybe I'll put a picture up here. V-shaped form, and then gliding before eventually touching down on the ground below. Now, they want to, of course, get the furthest distance, and as such, they need to be very aerodynamic and they need to be very fast. So let's start with the fast part. They're starting at the top of a hill, and they are then going down, the top of a ramp. They descend said ramp on their skis in their very skin-tight uniforms. Their velocity is going to be dependent on essentially the energy that they have at the bottom, and that is predominantly going to be dependent on their ability to travel along the snow and through the air while losing the least amount of energy, while at the same time converting the energy of being stationary at the top of this ramp to kinetic energy at the bottom, essentially taking all that gravitational potential energy from being very high and not moving and turning it into moving energy, going faster, right? So that is, of course, limited based on their weight, but they need to not lose energy on the way down. This is why they heavily wax these skis to decrease the amount of friction on the snow. By decreasing the friction on the snow, they will then lose less energy as heat on the skis. That's also why they try to keep a very regular positioning, right? If you deviate, then you can lose some energy, you'll lose some speed, and that will decrease your velocity when you jump. Then, of course, there is the wind in the air, which is going to be the largest factor. They deal with this by going ahead and they position their body by leaning down, having their arms back, and, of course, by wearing those very aerodynamic helmets and very skin-tight aerodynamic suits, right? By being in a very particular position, they can decrease the surface area of their body that is touching the air in front of them, right? There's all this air around them, so of course there will be air rubbing against their sides as they go down, which will cause some friction, but the majority of it is going to be resistance from all the particles in the air hitting their face as they sort of hammer through the air itself, right? So they want to decrease the amount of hammering through the air that occurs to decrease the amount of drag. To do that, you drop the surface area, right? There's less surface, which means there's less surface to touch that air. And by decreasing the surface that touches the air, there will be less drag pushing up against them. All right. So then they get down to the bottom of the ramp, they jump, and then they enter into the flight mode. They turn into flying squirrels. So the flight is where we see a lot of physics when it comes to ski jump, predominantly aerodynamics related physics. Am I an expert in aerodynamics physics? No, I'm not, but there's some very basic concepts, essentially aerodynamics. So when it comes to an object being aerodynamic, or I guess more so flying, there are three main factors. There is the lift, the drag, and the weight, right? If you've ever taken a course, and maybe in elementary school, I remember learning this in elementary school, is the lift is pushing the plane up, the weight is pulling it down because gravity, and the drag is essentially air resistance. It's what's sort of stopping it from moving forward very easily. So how do you manage that stuff? You want to essentially decrease your weight pulling you down. You want to increase your lift so that you stay up for longer. And you want to decrease the drag because the drag is going to prevent you from traveling further. Let me look at my notes. So the skiers aren't really going to be able to impact their weight. They have already done so by essentially wearing skin-tight outfits. So their weight composes of themselves and their skis. And so the big two factors are drag and lift, right? You, of course, want to be very aerodynamic. That's why they wear these skin-tight outfits again, right? Billowing things are going to cause drag, but they also need lift. And essentially, that V-like shape that you always see them come out with is very important for the lift. It was developed... I didn't write the date down. I believe I read it was in like the 80s or 90s. Someone developed that said posture, and it has been found that it causes a lot of lift, right? Essentially, you've increased your surface area, and that increase in surface area essentially allows the air coming in to kind of get captured and lift you up. Sort of like a flying squirrel, right? Or a glider. They come out, and any air coming in here sort of catches that pocket and lifts it up. There has actually been a scandal at the beginning of this Olympics. Well, so nothing has come of it, but there was, at the beginning of, as the Olympics were starting off, some scandal around the fact that there were rumors that people were causing their bodies to be changed in such a way prior to their suits being designed to allow for there to be more area on the suits. I'm not going to say the specifics because YouTube, but essentially the concept was, they're making parts of their body slightly larger because how the Olympics works is they scan the body and then produce the suits so that they are properly form-fitting. And that way, contestants don't design their suits in such a way that there will be extra pockets that can catch the air and allow there to be extra lift, right? Essentially, you don't want to go ahead and make there an extra pocket here so that they can open their arms up like someone who's jumped off a mountain in those gliding suits or like a flying squirrel and let the air sort of catch into that, right? That's kind of what they were trying to avoid. There were rumors that people were modifying themselves beforehand so that there'd be an extra few centimeters, and apparently that extra few centimeters would allow them to glide like meters extra, which is a huge advantage. But yeah, so it's very important that their posture be in such a way that they have a large enough surface area to cause a lot of lift, which allows them to stay in the air longer and allows them to travel further. This is why the skis that you'll see in ski jump look very different than the alpine skis or even cross-country skis. So yeah, the physics of ski jump is very aerodynamics focused. But now we're going to pivot to ice. So let's now go look at our next sport. Figure skating. That's right. We're going to now talk about putting blades on our feet and dancing. I do love watching figure skating. It's a lot of fun. You get to see some really cool artistic things. So there's a lot we can talk about when it comes to figure skating. A very classic physics textbook, science textbook example has to do with the posture, right? taking your arms, holding them outwards, putting them inwards, and how that impacts sort of how quickly they spin. Essentially, that has to do with the concept of moment of inertia, which is kind of the equivalent of mass when it comes to, we use like mass moving things forwards and backwards, but moment of inertia kind of has to do with rotating and spinning things, so angular momentum instead of like linear momentum. We're not going to talk about that. As cool as it is and as fun and kind of elementary as it is, figure skating is a great little sport for us to slide in and talk about ice skates, because ice skating is cool and there's a lot of really cool science there. And I'm a Canadian, and as such, I like talking about ice skating. This could have been hockey. I didn't make it hockey. You're welcome. So let's talk about ice. Ice is solidified water. Water and ice are essentially the same thing. They are made of the same molecules, H2O, dihydrogen monoxide. Two hydrogen and oxygen merged together. Water is matter. Matter has different phases, as you may be aware. The classic three. Matter classically comes in three forms: solid, liquid, gas. That's what you're going to learn about in school. Essentially, air is gas, water or any other liquids is a liquid, and then solid is like the table, me. I can poke myself, I'm a solid. Essentially, the properties have to do with how closely connected the molecules are, essentially those water particles, right? So in a gas, they're very dispersed. There is no sort of connecting forces. They all have a lot of energy. They move around. In a liquid, they still have energy, so they move and flow, but they're kind of bonded. That's how you can sort of put your hand through liquids, move through it, but the liquid is still sort of one substance. You're not really going to get pieces of liquid running away like you would with a gas. And then, of course, solid, they are so closely bound that they're essentially a single object. Usually get sort of like crystal formation. And so ice has crystals. Wow. That's why we have ice crystals. But there's a lot more to phases of matter, and there's a lot of other phases of matter. But what's important to note is that in thermodynamics, we have this thing called a phase diagram, right? Each of those three phases of matter, in fact, are not always going to transform at the same values. With water, for us historically here on Earth, we go ahead and say water turns into steam when it boils at 100 degrees Celsius. Water turns into ice when it gets to 0 degrees Celsius. It freezes. At our current standard pressure of 1 atmosphere, this is true. These are the temperature values where things transform. But it varies at different pressures. Essentially, a phase diagram has an X and Y axis where one is pressure and one is temperature. And if you vary the pressure or you vary the temperature, substances can transform, right? Like, for example, if we took a lot of gas, the gas particles have a lot of energy. They're moving all over the place. But if you put a lot of pressure on them and squish it down, you can turn it from a gas into a liquid. This is kind of one of the ways that we get cryogenic liquids. Now, of course, it is better for it to be temperature reasons that we lower it, but high pressures also impact the state. So it's kind of best to have a mix of both. That's why those liquid oxygen canisters are really high pressure, right? But on Earth, we're pretty much where we're at. There is at 0 degrees Celsius, we freeze. At 100 degrees Celsius, we boil. Of course, as I've said, this isn't always true. A good real world example that everyday people will deal with: if you go up into the mountains, your water will boil at a lower temperature. Anyways, skating. What does this have to do with skating? Well, when we skate, we have essentially gone ahead and taken a shoe and attached a knife to the end of it, or a blade, which is like a small strip of metal. Now, of course, those blades are actually cut in different ways, and we're not going to go into the specifics on blade cuts, but when they're cut, they are made to be very thin. So the thickness of said blades are pretty thin, like half a centimeter or less in thickness, depending on your type of skate, and very long. Now, you as a human have a lot of weight, and when you stand on these skates, That weight is now going to be transferred through your feet into said blades onto the ice. And well, that's a lot of pressure. In fact, the way skates are designed, it can be almost about 30 times the amount of pressure that we feel from the atmosphere located on the skate locations. So, everything else around it, that's fine. But where the skates are right there, that's a lot of pressure. And said pressure is being applied to ice. Now, by increasing that pressure, an interesting property of ice is that with more pressure, it will actually convert back into a liquid. And so what is essentially happening with ice skates is by you standing on said skates, you are applying a lot of pressure to the ice. That section of ice that is under your skate is turning into a liquid, or like bits of it are liquefying, which is going to make this surface smooth. As well, that said water is now going to fill in all those cracks in the ice as well, making it easier to skate more smoothly, allowing you to kind of cut through the ice. How does this rope all in? Well, of course, they do skating. They have blades on their feet when they do their dancing. But specifically, the properties of the ice are going to impact the sports. Softer ice allows you to do more interesting things, easier to spin on, easier to play around in, and that's why figure skating likes to have very soft ice. So they like to have an ice of about -4 to -2 degrees Celsius. This means it's very close to that freezing point, or that melting point, I suppose, if we're talking about going backwards to water. And that means that works for them. They need specific skates to meet the properties of both the sport, but also the properties of said ice. As another comparison, a very Canadian comparison, hockey uses an ice of about -8 to -4 degrees Celsius. It's much colder, it's much harder, but it is still soft enough that it works on the skates. If the ice was even more frigid, let's say -20 degrees Celsius, it might just crack when you step on it, right? It can be cold, but the reality of the fact is if it gets cold enough, the amount of pressure that you can supply isn't actually going to convert it back into water, and it's more likely to damage the ice. It's going to actually make it very hard to skate on. So this is why sports like figure skating like using softer ice. So now that we've talked about the science around figure skating, some of the science about ski jump, I need to do a Canadian thing. So our last sport is you thought I was going to do hockey. I know you did, but no, I am a curling fan. This is my scarf. Go Team Canada. This is my empty mug. Love me some curling. I used to be really big into curling. I used to play it all the time. I used to be a little bit competitive. Oh, this is getting a little bit itchy. Yeah, I love curling. Well, one, because I just played it a lot. Two, because I'm Canadian. It is pretty popular here. It isn't hockey. It doesn't hold a torch to how popular hockey is, but it is really popular here. There are a lot of very good teams. A lot of the international teams come to Canada to play and spend most of their time here playing in curling bonspiels. It's a big deal. There are so many very good teams in this country. But number 3, my third reason for loving curling is that it is just interesting. Essentially, for those who don't know, the best way to describe curling is like, imagine the concept of darts, but also bocce ball is done on ice, but you can also cause the ball to shift. And then there's some chess elements involved because you're playing against other people actively. It is very cool. But there is also some really cool science to it. In fact, people on the internet love to talk about the fact that science doesn't understand curling. It is very interesting. Essentially, all curling stones are made from granite from a specific island in Scotland called Ailsa Craig, which is a bird reserve and is off the coast of Erin, I think. Anyways, southern Scotland, western Scotland, on an island that has a lot of birds. They harvest it for granite. They use that granite to make curling stones or curling rocks, and they play. But the curling rink is designed in a very particular way as well, ice-wise, and you rotate said stone, and there's a lot of just really neat little physics stuff going on there. I could do a whole video on just the science of curling. There's a lot of papers that I read components of about pieces of curling, sweeping, playing. There's a lot of stats that you can do to kind of decide how it's appropriate, but we're here to talk basic science. I'm here to introduce these three sports to you, and this one's my favorite. Go Gushu. I know he's retiring, but Gushu, you're my favorite. So let's talk about the science of curling. Particularly, I want to talk about the science of how the rocks curl, because that is the namesake of the game. But first, let me kind of introduce the concept of curling to those who don't know. Let me introduce you to kind of the basics of curling. And I'm going to not talk about mixed doubles. Mixed doubles is great, but most curling that you're going to watch is going to be the normal 4-person curling games. All this physics still applies to mixed doubles. I just want to kind of talk about this, and this is the one that most people are going to watch. So in a curling match, you have 2 teams of 4 people, and each person is going to throw 2 granite stones or curling rocks down the ice. So in a total, 8 rocks are going to be thrown per end. There are multiple ends. Each end is scored. You are throwing said rocks down a sheet of ice that is 42 meters by about 4.5 meters. And they are thrown down and landing in sort of a target. As a team, at the end of the end, you score points based on who has the closest rock to the center of said target or the button. Right? The team that is closest to the button, their rock counts, and then the next rock that is theirs that is closest counts as well. So essentially, it counts out from the center rock. That might have sounded a little bit confusing. Essentially, the concept is there are 2 colors, let's say red and yellow. Those are usually the colors. The red stone's on the button. It is closest to the middle. The next rock is also red, that's closest. So the next closest rock is red. The rock after that is yellow. Red scores 2. That's because they have the closest rock, and then the next closest rock is also theirs, but the rock after that isn't. If that other rock was also red, then they would score 3, etc., etc. You don't always need to put a rock in the house. Lots of strategy. We're not here to talk curling strategy. We're here to talk science. Okay, so when we talk about throwing those rocks, this is where the cool stuff happens, right? People sit at one end, they aim at a target, and they come out, and then they release the rock with a handle. You either do it clockwise or counterclockwise, and essentially they put a spin on said rock. This spin allows the rock to curl, or essentially move out to the left or right-hand side, allowing you to kind of aim for your rock to come down the ice and go around other rocks to go in. Now, how said curling works, that's where the cool stuff happens. So the direction of the handle causes the rock to spin, while it is also moving down the sheet. Now, when it spins, what happens is, vaguely speaking, we get 2 regions of friction, or essentially 2 coefficients of friction. The coefficient of friction is a property that we have to physically measure. It's not something that we can calculate pretty much, but the surface has a coefficient of friction. It's a way to kind of tell how much friction you would feel on a substance. The forward rotating side of the rock ends up having a lower coefficient of friction than the backward rotating side of the rock. Essentially, to the rock rotating and spinning, you're getting some rubbing on the ice, along with the rock moving forward. Said rubbing from both directions allows there to be heat. Said heat melts the ice a little bit. So by melting it in those specific regions, you get more melting in that forward rotating region than the backward rotating region, allowing there to be 2 coefficients of friction. These 2 coefficients of friction allow there to be a difference in kind of how fast each part of the rock is moving, which allows it to curl. So that's pretty cool. Essentially, we're causing there to be 2 spots on this one solid object that are moving at slightly different speeds, allowing it to kind of spin. That's pretty neat. But in curling, there is not just a guy throwing a rock. You may have noticed the people with brooms. essentially they sweep the rock, right? There are 4 players. One person is, setting up the target line. One person is throwing. The other 2 get to sweep. And the sweepers can influence how the said rock moves, right? Let's say that I release the stone and I have made it not curl enough for some reason. Well, because it's not curling enough, we could try to make it curl more. And by doing so, it would be the sweeper, who is near that forward rotating side of the rock, would sweep more. Essentially, the concept of sweeping is both to clean the area in front of the rock, preventing like things getting in the way, frost, dirt, things getting under the rock that would impact how it moves, but also by sweeping, you're putting a lot of energy into the said location, melting the ice. That allows that coefficient of friction to change. And so if we change our ratio on the coefficient of friction, that can impact how said rock rotates, right? Essentially, we can make it rotate more by increasing that difference or decreasing that difference to make it go more straight. That's really cool. But there is, of course, a downside. You have added more water in front of said rock, decreasing the friction overall, which means it's going to travel further, right? So you can make it go further, but it may not spin as much, or it may spin more depending on where you're putting that sweeping, right? If you sweep across it in general in both directions, it may just curl as much as it was going to before, but it would go further. If you sweep only on that backward facing side, it may go more straight. More on the forward facing side, it may curl more. There's a lot of nuance, but essentially asymmetry and friction allows curling stones to curl. And that is pretty darn cool. So we've kind of talked about sweeping. We kind of talked about how the rocks move. There's a lot more we could talk about, but of course, this is supposed to be sort of an introduction video. But I want to just quickly talk about curling ice. We talked a lot about ice in the figure skating section. Curling ice is cool because they do the thing called pebbling. Essentially, the ice is prepared beforehand. You have the flat sheet, but they apply the stuff called pebble. Essentially, a guy puts on a Ghostbuster-style big backpack and holds a stick, which has like a watering can kind of cover at the end, and flips it back and forth while going down the ice. And essentially, you cover the ice in a bunch of drops, right? You want a very consistent set of drops. And this pebbling has an impact on how the rocks move. How the ice is pebbled impacts how much curl and how little curl occurs in a game, as well as how easily the rocks travel down the sheet, right? Studies found that essentially if you have pebbling, there will be a moderate curl on a stone, and the stones will travel a reasonable distance for a normal curling game. But if you don't have any pebbling at all, those rocks will curl a lot more, but the stones will not travel anywhere near as far. And so that's very interesting. Essentially, by changing your ratio of pebble, your quality of the pebbling, you can impact how easily rocks travel down the sheet. That's why if you ever look at curling in these big stadium games like the Olympics, the ice is different than at your local curling club. Stadium ice is different, and you hear the commentators talking about that sometimes. So it is very important that the players who are curlers practice on the ice and learn the properties of it so that they can adapt their game, adapt where they're applying that pressure when sweeping, adapt how much energy they're putting into the stones, how much spin they're putting on those stones to allow it to curl appropriately. And that's kind of the science of curling. Very basic. We could do, again, a whole video on that. And if you want a video on the science of curling, leave a comment because I will do it. I love me some curling. All right, so those are our 3 sports. Welcome to the Olympics. I hope your country gets some gold. I hope Canada gets some gold. And we have an interview hopefully coming in our March video series. And there will, of course, be another one, non-interview episode like this, where I talk about science stuff. In the meantime, if you like this video and you want to see more, leave a like, give a subscription, ring that bell. It allows you to support the channel. It allows me and my videos to hopefully reach more people. And eventually, if we can up our subscriber count, then maybe I can start to monetize the channel, and that money can come back into these videos, allowing the production value to hopefully move up. I've learned a lot in the last little while, and thankfully these have been improving, but there's always more that we can do. I hope you have a lovely Olympics, and take care. I'll see you in the next video. Bye, everyone.